All right. Number one thing we're talking about, topic zero, is what is a virus and how do we get sick? I'm covering a lot of stuff that I've already talked about previously, live on stream. So that's why it's called topic zero. But I'm going into a little bit more detail that's going to help us understand some of the other stuff that I'm going to talk about later. But let's see. Let's start with, and these are just my notes for what I'm going to cover. So it says picture of a virus. We're going to look at a picture of a virus. This is obviously not an actual photo. It's a computer generated image based on electron microscope scans of what a virus looks like. So if you could actually get down to that level, light is light waves are too wide for us to actually see what things look like. So they have to propel little electrons and bounce them off and generate an image. Anyways, not the point of what I'm trying to talk about. But we have a picture of a virus. I think I looked up coronavirus. In this picture, you see these little red nodules. And what these little red nodules are going to be really useful for us to identify a virus. And so what scientists call these, they call these, I'll use my pen, antigens. But the whole point is that they just came up with a name for something that we can recognize. So these little nodules that come off of it are known as antigens. Um, so viruses, number one fact, we're only covering 2.5 things today for this topic, is that viruses have markers on them and we call them antigens. So number two is there's a specific type of cell in our body, a white blood cell called T cells, and they have a special feature. They have a memory um, so that in our bodies they can recognize those markers on viruses and tells other cells to destroy these using antibodies. So if we zoom out, here I drew a picture of a T cell with glasses on it, basically just to illustrate the idea that once these cells can recognize, draw it from its eyeball so we can tell, these antigens, it's going to start telling people, hey, hey, danger, danger. That's what the purpose of this T cell is. And so once this T cell does its job, what happens? Well, it tells the body to make antibodies, and those antibodies destroy the cell. Use orange. Totally destroy. How it destroys it, not super important. Things attached onto it, things sometimes the viruses get ripped apart. Sometimes cells no longer accept the virus from entering the body. Those are just minor details to things that we're not focusing on today. But how's that important for us right now? It's important because we can, as scientists, um, use these markers taken from viruses, either by destroying or weakening the virus. We can then basically insert those destroyed pieces into a body so our T cells are prepared for fighting this virus long before the virus actually gets there. It's basically like sending an early message. That's the entire gist of what a vaccine is. So, to those disabled pieces of viruses, when they're injected into our bodies, that's what we actually call a vaccine. And the process of creating vaccines and testing them for effectiveness and safety, that usually takes between 2 and 8 years, depending on how deep and how quantifiable all of our data that we want to collect is. So, drug and vaccine testing, the rule of thumb is that the larger the group, the longer it takes. And the reason for that is because if it only affects 1 to 2, say, million people, then one, it's less urgent, and two, it doesn't impact, the rest of the 200 something million people, probably 300 something million people living in the United States. So how in-depth the testing is does not have to be as deep, and it doesn't take as long. And that's for most drugs. Most drugs probably only take 4 or 5 years to finish all phases of their testing, which I'll talk about in a little bit. With vaccines, the problem with vaccines is that vaccines can affect everyone. And if it's a vaccine you want to give everyone, which is super relevant for what we're talking about today with coronavirus, which everyone wants the vaccine, unless you've already gotten it and you're already immune, uh, which means that's affecting 300 million people. So with that in mind, we're going to talk about why it takes so long to make these vaccines. Scientists in a lab can break a virus piece um, or weaken a virus probably in a matter of like 15 days. That's not the difficult part. The difficult part is making sure, again, that it's one, safe for humans, and two, it doesn't have any other possible effects. So, in order to do that, we have to go through quite a few phases. The first phase is the experimental phase, is that they're testing these vaccines, these broken up virus chunks. They're injecting it into animals first, and then seeing what happens. Okay, nothing bad happens. We're not even testing to see if it has a positive effect. We're just seeing to see if there's no negative effect. And once it's safe, then there's another step, um, seeing if it actually helps, right, against the virus. So there's two stages to that. Once you're done with animals like mice and rats, then they have to move on to human-like animals because it could react differently. This vaccine could react differently in different creatures. So we haven't actually tested in humans yet, just mice and rats. Then they tested in human-like animals. This could be like monkeys, apes, bonobos. Is that how you spell bonobos? I'm not sure. Bonobos. See what happens first, and then see if it actually helps. Phase one, done. Took a few months maybe. Phase two, this part is where a lot of places get stuck because you have to prove almost without a shadow of a doubt that it's extremely safe and there's no other possible um, features or dangers to this vaccine or drug that you're trying to produce. So this is usually done in universities and major hospitals. Before it was done in university labs and pharmaceutical labs. These are called clinical trials. They do small sample sized non-exposed humans for viruses. So if you're not exposed to this dangerous virus, they're going to test you first. And this is probably sizes of like 20 or so people. Once that's done and proven to be safe, then they do small sample size to humans that may be exposed either purposely or accidentally. Um, and again, sample size very small, maybe 20 or so people. Then they expand to large scale trials. And this, they only move on to the next step once it's been shown that there's no possible negatives. This is why a lot of things don't get past this phase because there's sometimes a lot of side effects that are not good for people. Large scale, trial one. And then large scale trial two compares it across different geographic and environmental areas. That's when you need to expand it outside the country, outside of, say, California, if they're testing in California, all over the place. If you can get past this phase, then you enter phase three, which is arguably harder. They just keep getting harder. Um, all of phase one and two, they get repeated under these organizations: the CDC, Center for Disease Control, WHO, World Health Organization, and FDA, which is the Federal Drug and Agriculture Administration. Um, you have to do all of this again, but under these organizations. Then once it passes, then will they finally do production of these drugs and vaccines? But then they're not done. They have to repeat phase one all over again, phase 1 and 2. Oops, 1 and 2 repeated for the third time for quality control. Because what if these companies that are actually producing it didn't actually meet the criteria to make it safely? They have to test all of these for the third time. But arguably, this is shorter than the first two. And then finally, in phase 4, are you allowed to send it out to the public while still doing ongoing studies for the next 10 to 30 years? So why this is so important, why it has to go through all these phases, I'll just go through some scenarios. What happens if they do it wrong? Maybe they didn't weaken the virus enough, because one of the options is we could just weaken this virus so it doesn't hurt you as much or it doesn't kill you. The regular flu vaccine that we get every year, if you'd like to, obviously optional, is attenuated, which is weakened, so we can get those antigens so we're ready. Um, but what if they didn't make it correctly? We weaken it, but it gets stronger, or we didn't weaken it enough, and it just kills a portion of people that get that vaccine. Or um, it could make people more likely to get sick because it actually weakens us too much. Or um, that vaccine could pick up genetic material from a different disease because they didn't account for that. That could also kill us. And then also, maybe it doesn't work well with another essential medicine or drug. Maybe you have diabetes and you have to take something. It doesn't mix well with that vaccine and actually makes you sicker. All of these things, and this is just Mr. Yao coming up with this off the top of his head, and these are all real situations that he's learned about. Um, these are all situations in which are hyper realistic. They've happened with other vaccines, and that's why they don't make it through all these phases. That's why they've made all of these phases necessary. That's why it's going to take a really long time for a vaccine to be safe and distributed to the public. My guess is slightly less than 2 years is probably the most optimistic guess. Um, I'm going to increase the screen really quick so I can see myself. Not just so I can see myself, but because I want to talk about the smallpox vaccine. Essentially, uh, definitely maybe your parents, definitely your grandparents, um, all had a shot when they were babies for the smallpox vaccine. And it's considered essentially extinct at this point because every single person, enough people in society, the world, have immunity to that disease that that disease can't travel to other people anymore. So it's essentially considered extinct. And so let's see his arm on here. If you take a look right there, there's a little scar. That's a scar from a smallpox vaccine that he got because he was born in China. And China continued having those smallpox vaccines, I believe, until 1994. Don't quote me on that. All right, thanks for joining us.